Well, greetings, students. Dr. Matroka here. Today we're going to be covering a new unit, which is a little bit of a challenge and requires some uh, physiology background in order to make heads or sense of it. And that is the autonomic nervous system and neurotransmitters and physiology involved in that system. This is just a list of abbreviations that you may want to refer to because some of these terms are rather lengthy and it saves time to just refer to them by abbreviation. Now this is a list of learning objectives. You can go over that on your own. Okay, so the overall nervous system, as you see here, it's broken down into the central nervous system, brain and spinal cord, and then you have the peripheral nervous system. Now, part of the peripheral nervous system is the somatic or the voluntary nervous system. This is basically what corresponds to skeletal muscle, so voluntary movements. And then in contrast to that is what we're going to be talking about, the autonomic. And notice this does not say automatic, although that it's a similar term. The autonomic nervous system and its two divisions, the sympathetic and parasympathetic. So what is the autonomic nervous system? Well, it's a series of nerves that travel to smooth muscle and cardiac tissue. In other words, cardiac tissue is your heart. And as you see here, it's primarily a motor system, okay? Motor meaning actions as opposed to sensations. And it involves involuntary muscle contraction. Now, it's something that many of these slides are taken out of your book, Chapter 5. Something that they note and is worthwhile for you to know is that muscle tissue, this is involuntary muscle tissue, I should have spelled that out, has its own kind of contraction, ongoing level of contractility. And if you look at this peristalsis video at the bottom, you'll see how in the intestine you'll always have waves of motion going through the intestine. It's really an unbelievable thing to see in person where it propels food through the GI tract. And that's part of what is autorhythmicity. And so the ANS basically regulates the rate at which internal organs work. And the main thing it does is it maintains homeostasis. Okay, when things get a little bit out of balance because of external impacts on our life, the autonomic nervous system tries to correct for that and get you back to some sort of a steady state or homeostasis situation. Now, the ANS is broken up to two somewhat discrete regions. One is called sympathetic, the other is parasympathetic. And the main thing is that the two have opposite effects, generally speaking. And most organs, not all, but most organs have dual innervation. Okay, they have input from both the sympathetic and the parasympathetic. And the two that you really want to remember the most are the heart and the lungs in that respect. Okay, so this is a poll I would have taken in class, but I'd say, turn off the PowerPoint slide forwarding and take a look at this and answer it on your own. Now, let's look at the parasympathetic division first, okay? That's really a little bit easier. The nerves that come out of the central nervous system, okay, come from the brain and the lower spinal cord, all right, for the parasympathetic division. I have an image I'll show in a few minutes, okay? And this division tends to be more involved in maintaining a sense of rest and restoration of body energy sources. And you could say it involves bodily functions such as digestion, elimination, waste products. And this is kind of an important thing. The innervation tends to be discrete. okay, localized. So with the parasympathetic, your brain can tell your urinary bladder to contract or your heart to slow down independently. Okay, so those things can be monitored and dealt with independently by parasympathetic outflow through different nerves. Now, the kind of the little acronym or way to remember the parasympathetic nervous system actions is think of it as rest and digest. So here's the parasympathetic nervous system showing, this isn't the best diagram, but it's one I got from your book, so you can refer to that. And it shows you that the outflow from the central nervous system is via these cranial nerves, okay, which are at the brainstem, and then you go way down here to the sacral level, okay. This is often called a craniosacral output. And you see that these are the different end organs that are innervated by the parasympathetic. Main ones being heart, lung, eyes, GI tract. Now, one little mnemonic that I always remember hearing with respect to the PSNS is the idea of SLUD or SLUD syndrome, which kind of captures some of the main actions. So, activation of the parasympathetic nervous system causes salivation, lacrimation, urination, and defecation. Hopefully that will help you remember the actions. Now we turn to the sympathetic division, which is a very, very important aspect of our nervous system. Now these nerves originate kind of from the central part of the spinal canal. It's called thoracolumbar areas. And the excitation of the sympathetic nervous system leads your body for action. And again, our two main organs are the heart and lungs, so it increases heart rate and force of contraction, and it causes bronchodilation. Those little alveoli and actually all the bronchioles in your lung kind of dilate. Dilate means widen to allow more air to get in. So you have your heart beating faster, more ventilation, and that allows you to be prepared for action. Okay. Now here the effects are somewhat diffuse. In other words, the sympathetic nervous system tends to be an all or none thing. It either is activated or it's not, and when it's activated, most of the target organs are activated. Now, another aspect of the sympathetic nervous system that is very important, that the nerves, or some of the nerves coming from the sympathetic nervous system, lead to the adrenal medulla. And the adrenal medulla releases epinephrine into the bloodstream when the sympathetic nervous system is activated. And that again is part of the sympathetic nervous system response. Overall can be considered a fight or flight type of action. Okay, so activation of the sympathetic nervous system, the neurons themselves, okay, synapse with the heart and the lung, causing the heart to go faster and stronger, and the lungs to inflate better, and then it causes the release of this epinephrine from the adrenals, which circulate throughout the body. Epinephrine is also called adrenaline, and that's a hormone that acts synergistically with the local neuronal output to result in this fight or flight kind of activity. So here is a diagram again from your book showing the outflow from the central nervous system, and you can see that the neurons again start within the spinal cord, and then they go out to the various organs. And see, you can see many of the organs that we saw on the parasympathetic, being innervated here because of that concept of dual innervation. So this is just a figure that I pulled off the internet that I think does a decent job of showing you the effects of activation of the parasympathetic versus the sympathetic. Okay, so really though, if you remember this rest and digest for parasympathetic and fight or flight for sympathetic, you'll be able to anticipate what most of the effects are in terms of the individual organs. For example, you know, sympathetic here, you can imagine somebody who's surprised and their sympathetic nervous system kicks in and their pupils are dilated, right? They feel dry mouth, have that racing heartbeat, and breathing faster. Okay, so you can kind of get a pretty good idea of what's happening just using those two simple mnemonics. Okay. Now, another aspect of the ANS that is very important is its impact on blood vessels. Okay, and primarily they're arteries, but we're going to take it from the point of view of blood vessels, generally speaking. Not so much capillaries, but the larger blood vessels leading to capillaries. Now, the blood vessels themselves actually have smooth muscle in them. Okay, and the smooth muscle can contract. When it contracts, it reduces the volume inside the area inside the blood vessel, what we call the lumen. It reduces that when it contracts, and when it dilates, okay, when the muscle expands, we get what we call vasodilation. This is vasoconstriction, vasodilation. All right, and this is going to come in very important later on when we're talking about blood pressure. So it's worth noting. And the vascular tone, okay, the degree of constriction versus dilation, is almost completely determined by the sympathetic nervous system. So this is in contrast to what we've been saying up to now, that you have that duality of function. Okay, here we tend to have almost everything, all the level of vasoconstriction or vascular tone determined by whether the sympathetic nervous system is activated, which causes contraction, or it's not activated, which causes dilation. I like the way they have this here, that these little bars coming up show you the neuronal activity. This is high neuronal activity, this is low neuronal activity. Okay, constriction, dilation. So you can look at this on your own. It's just a comparison of sympathetic and parasympathetic stimulation. Again, the main ones that, well, actually all of these are pretty important. I know adrenal, medulla, we talked about that, arteries, heart, GI tract, pupil of the eye, respiratory passages. Okay, those are really the main things, and we're going to keep coming back to this later, but it would be a good idea if you can start to kind of remember some of the aspects in this important table. So here's another one of these questions that you can answer on your own. Now, another important aspect of the ANS is the way the nerves connect. Okay. Now, in the somatic nervous system, a neuron comes out of the spinal column and goes directly to the skeletal muscle. It's sort of one neuron. But in the ANS, okay, you always have two neurons working together. So the primary neuron, the one I'm calling a primary neuron, is the one that exits the spinal column there, that neuron from the CNS, synapses with a second neuron, okay, that leads to the target organ. Now, these neurons tend to, the primary neurons tend to be grouped together, and there's collections of synapses. Those collections of synapses are called ganglia. Okay, so those are discrete areas. You can actually find them anatomically, these groups of synapses in the body, and they're called ganglia. Okay, the primary nerves, okay, again, that's the ones coming right out of CNS, are called preganglionic neurons, and the secondary nerves, the nerves leaving the ganglia, are called postganglionic neurons. For some of you, that's kind of like, whoa, what are you talking about? A little bit strange, but kind of try to get used to hearing the terminology. A diagram will explain it a little bit better. And we're going to get to the diagram. Now, the other very important, probably the most important aspect from terms of pharmacology is the neurotransmitters, okay, that are acting in the nervous system. And if you're not familiar with the concept of a neurotransmitter, I recommend you go back, look at a basic biology book, and make sure you kind of have that understood. All right, but a neurotransmitter acts on a receptor to cause an effect. All right, so you have neurotransmitters that go from one neuron to another, and then you have neurotransmitters that go from a neuron to an effector site. All right, like a neuromuscular junction where the neuron connects with the muscle. But we're going to talk about the types of neurotransmitters in the ANS, because those are what's affected by pharmacology, which we'll talk about in our subsequent lecture. So the neurotransmitter at all preganglionic neuron terminals, that is synapsing in the ganglia, and also at the adrenal medulla, is acetylcholine. So this is a little tricky, but the preganglionic neurons, there's some of them that come out of the spinal cord, synapse directly onto the adrenal medulla, and it's kind of like a type of ganglia, and they all involve acetylcholine. Now, the neurotransmitter at the postganglionic neuron terminal, the end where the postganglionic neurons synapses with the effector site, is either acetylcholine, and that's for the sympathetic neurons, okay? Excuse me, my mistake. Acetylcholine for parasympathetic neurons, or epinephrine for sympathetic neurons, okay? I think this diagram does a nice job of summarizing a lot of this talk, which is really hard to understand in just without having some visual. So first of all, let's start off with somatic nervous system. Okay, so here is a cell body, the beginning of the nerve, in the central nervous system. It leaves and it goes all the way to the effector site, all right, which is skeletal muscle. So this is just for comparison to the ANS, and it turns out the neurotransmitter there is acetylcholine. Now let's look at the autonomic nervous system. We'll start with the sympathetic branch of it. Okay, again, notice that in the ANS we have two neuron chain from CNS to effector organ. All right, so here we have for most of the neurons coming out of the sympathetic neurons coming out of the spinal cord, the preganglionic releases acetylcholine, we know that, and then there's the postganglionic fiber, which releases norepinephrine at the effector site. This is the exception, well, not really exception, but this is the alternative that I mentioned earlier, where the preganglionic neuron, sympathetic neuron, synapses with the adrenal medulla and releases acetylcholine to have the adrenal medulla release primarily epinephrine. Okay, primarily epinephrine into the bloodstream. So you can see that in a sense, the adrenal medulla is kind of, I don't know, it helps me to learn it this way, kind of like a pseudoganglion, if you will. All right. Then we have the parasympathetic nervous system, where the cell bodies are in the CNS. Again, different location than the sympathetic, but they're still coming from the spinal cord. And then they synapse again on the ganglia, releasing ACH. Now, the postganglionic neuron releases acetylcholine onto its effector site. Okay, So there's a lot in this diagram, but if you can kind of capture most of it, you'll really have a good idea of what's going on. I'd recommend you try to draw this on the board yourself and fill it in, explain it as if you're explaining it to someone, and you really kind of have a good understanding of pretty much everything you need to know about neurotransmission in the ANS. So kind of drilling down on this a little bit more in terms of the neurotransmitters, acetylcholine, that neurotransmitter of the parasympathetic nervous system, activates what we call cholinergic receptors, okay? And the word choline being choline coming from acetylcholine, right, receptors, okay? And compounds which act like it, which we're going to be talking about in terms of pharmacology, agonist of ACH, are cholinomimetics. Then we have norepinephrine and epinephrine. Okay, remember, norepinephrine is the neurotransmitter. Epinephrine is the hormone released from the adrenal medulla. They bind to and activate what are called adrenergic receptors. I think the term adrenergic comes from adrenal. Okay, so, but either way, when you hear about the sympathetic nervous system, you're talking about adrenergic receptors. And the agonists there are called sympathomimetics. Sympatho meaning sympathetic nervous system. So here are some structures of the neurotransmitters. We're going to be going into much greater detail about these structures and how they relate to agonist, antagonist, when we talk about the individual, the pharmacology of the sympathetic and parasympathetic nervous system. But for now, at least you just get an idea. So here's acetylcholine, the cholinergic neurotransmitter. You see it's a really very simple molecule. This is the acetate, and this is the choline part of it. Okay, and then we have adrenergic neuroactive substances. One is norepinephrine. This is actually the neurotransmitter. This is what's released by the postganglionic sympathetic neurons. And then we have epinephrine, which is released from the adrenal medulla. But both of these, okay, tend to activate similar set of receptors. So they're called adrenergic agents. You can take a look at this question and do it on your own. And again, we're going to talk about this in more detail, but just so you have an idea. The receptors can be broken down into different subtypes. So a long time ago, when people were looking at these receptors pharmacologically, they found that you could have compounds that would activate some of the receptors, but not others. For example, acetylcholine, right, would activate all cholinergic receptors. All right, that's kind of goes without saying, I think. But there's a compound which was isolated from a certain kind of mushroom called muscarine, okay, which was found that would only activate visceral organs and glands that are part of the parasympathetic nervous system, right? So they were able to say, oh, there's two distinct populations of cholinergic receptors. One of them called muscarinic that are activated by muscarine, and then another group called nicotinic that are activated by nicotine, okay? So the nicotinic receptors are distinct from muscarinic, but they're both activated by acetylcholine. So nicotinic receptors are located at the ganglia, all ganglia, sympathetic and parasympathetic, and on cell membranes of skeletal muscles. Okay, so where neurons, somatic neurons junction with skeletal muscles, what we call a neuromuscular junction, they're nicotinic receptors. So I don't want to get into the detail of the adrenergic receptor subtypes right now, but suffice it to say that we have alpha adrenergic receptors and beta adrenergic receptors, kind of along the lines of with the cholinergic receptors, the way that those two populations were teased out. Pharmacologists were able to tease out these different kind of subreceptors of adrenergic subreceptors. There are actually even further breakout of these, but for our purposes here, we're going to stick with really alpha 1, beta 1, and beta 2. And you can kind of get an idea of what happens when you activate these different receptor populations, but we're going to go into that in detail when we're actually talking about the sympathetic nervous system. I like this diagram because it does kind of a nice job of showing you where the neurotransmitters are in the various portions of the ANS. So here we're looking at 3 different preganglionic neurons, okay, and what happens with them. So this one, okay, remember craniosacral is the parasympathetic, so this is kind of the cranial area, and here we have a preganglionic neuron synapsing at a ganglia, and sure enough, acetylcholine, and it happens to the N means that it's a nicotinic type of receptor. Acetylcholine is released there, and then on the effector, which would be like, for example, cardiac or smooth muscles, the acetylcholine is released, and the receptor type here is a muscarinic receptor. Okay. Now, if we look at the asympathetic, 2 different sympathetic preganglionic neurons, here's one again. You always have nicotinic cholinergic receptors at the ganglia. Now here's the postganglionic neuron. You see its synapses. Uh-oh, this is a little unusual. I hope you see this. And I am going to kind of hold you accountable, if you will, for this. It is a little bit of one of these one-offs. But you notice that we have sympathetic nervous system outflow where there's acetylcholine released onto the neuroeffector, okay, onto the sweat glands. This is a oddity about the system because generally speaking, the sympathetic nervous system, the postganglionic neuron, releases norepinephrine on every single effector except the sweat glands. Okay? Now, that's important because later on we're talking about botulinum toxin, which many of you may be interested in. We'll talk about it. It's relevant how this distinction. Okay? So again, just to go over it. Parasympathetic, we have acetylcholine at the neuroeffector. Sympathetic, we have norepinephrine at the neuroeffector. That's the general statement, okay? If I ask you, what do most postganglionic sympathetic neurons release as a neurotransmitter? It's norepinephrine. But the exception is sweat glands. Sympathetic outflow, because that's defined from where the neurons originate. But the neuroeffector neurotransmitters is acetylcholine acting on muscarinic sites. Okay, you can answer this on your own. And just to kind of summarize where we're at here, this little diagram kind of gives you a summary of what's what. Okay, there's a lot of material. I hope you can digest it. Feel free to go back and review, and we'll be using much of this information for the next couple of lectures regarding pharmacology. Okay, take care, my friends. God bless.